current electricity, we are having a very important concept in the form of Wheatstone bridge, meter bridge and potentiometer. Already we have taken up few applications. Let us work out few problems even on those concepts as well. Next question, that is problem number 21. Let me read out that one. A metallic conductor at 10 degrees centigrade connected in the left gap of a meter bridge gives balancing length 40 centimeter. When the conductor is at 60 degrees centigrade, the balance point shifts by 5 centimeter. The temperature coefficient of resistance of the material of the conductor is, that is a question. He gave 4 options. Very first option is 1 by 210 per degree centigrade. The option 2 is 1 by 220 per degree centigrade. Option 3 is 1 by 200 per degree centigrade. And fourth option is 1 by 201 per degree centigrade. But officially, by all means, the correct option is A. Let us check how we get the first option as the result. All of you can straight away understand this particular problem is linking meter bridge concepts with the effect of temperature on resistance of a conductor. Such type of linked up models are very common at JEE level. So let us take the question once again. A metallic conductor at 10 degrees centigrade connected in the left gap of a meter bridge gives balancing length 40 centimeter. So let me write the same concept over here. At 10 degrees centigrade, that's what has been given. The balance length is given 40 centimeter. That is what is the data provided to us. When the temperature has become 60 degrees centigrade, balance point shifts by 5 centimeter. You can all understand first and foremost, when temperature increases, resistance of a conductor certainly increases. When resistance increases in the left gap, automatically the balance point also will be increased. That means what? The balancing length increases by 5 centimeter. That means earlier it was 40, now it becomes 45 centimeter. So it increases by 5 centimeter, it will not decrease, remember that point carefully. So we can write this one now is becoming 45 centimeter. For this given data, I just write 2 equations. First equation over here is R at 10 degrees centigrade by unknown resistance in the right gap of the meter bridge. I consider that one as X. So R10 by X is equal to 40 by 60. You can write that one as 2 by 3. This implies what we can write now? R at 10 degrees centigrade is directly proportional to 2 by 3 now. That is what actually I can take it for granted. The next one over here, if I take the second one, R this time at 60 degrees centigrade by unknown resistance being X. This now can be written 45 by 55, which of course you can write this one as 9 by 11. So what I can write now directly? R60 is proportional to 9 by 11. You can even take these equations directly also. There's nothing in that. But we have been asked here to calculate the value of alpha. What is alpha? The coefficient, temperature coefficient of resistance. That is what actually is to be finalized from the given data. So let us take here alpha is equal to R at 60 minus R at 10 divided by R at 10 into T2, that T2 is 60 degrees minus R at 60 degrees into T1, that now becomes 10. So you can understand what exactly the equation I have taken up. R2 minus R1 by R1 T2 minus R2 T1. That is the formula. Out of all, we now can directly write the values. R60 minus R0 proportionality values directly can be taken up. 2 by 3 minus 9 by 11 by 9 by 11 into 60 minus R60, that is of course R10 first, it is 2 by 3, I just should write like this, R60 minus R10, that is 9 by 11 minus 2 by 3 divided by 2 by 3 into 60 minus 9 by 11 into 10. If you simplify this particular equation, you will be getting 1 by 210 per degree centigrade you will be getting. So 1 by 210 out of all the 4 options which are provided to us in the problem, this coincides with the very first option for us, that is given as 1 by 210 per degree centigrade. So what will now be the correct answer for this one? The answer is A itself. But all of you should understand from this model, the effect of temperature on resistance of a conductor we know. That is now linked with the experimentation with meter bridge in this particular problem. So such models are very, very common in different entrance examinations. It of course is useful for you even at JEE level also. At mains level we can expect such model as well. So the correct answer for this question number 21, that is 1 by 210 per degree centigrade. Let us switch over to problem number 22. Two unknown resistances X and Y are connected across the left and right gaps of a meter bridge, and the balance point is obtained at 80 centimeter from left. When a 10 ohm resistance is shunted across X, the balance point is 50 centimeter from left. The values of X and Y respectively are, as usual, 4 options. First option 40 ohm and 9 ohm. Second option 30 ohm and 7.5 ohm. Third option 20 ohm and 6 ohm. Fourth option 10 ohm and 3 ohm respectively. The correct answer for this problem is the second option, that is 30 ohm and 7.5 ohm as such. But what exactly the question? Look at once again. Two unknown resistances X and Y are connected across the left and right gaps of a meter bridge, and the balance point is obtained at 80 centimeter from left. Let us write the data here. In the left hand side gap we have X. In the right hand side gap we have Y. And of course, length he has given 80 centimeter, that is balance length. 80 means what will be the remaining? Obviously 100 minus 80. So L2 must now be 20 centimeter. Then what I can write according to the concept of Wheatstone bridge balancing principle? What can we write? We write x by y is equal to 80 by 20, which now is going to be 4. So what we can understand from this one, there is a relation between x and y like this. What is the relation? X is equal to 4 times y. That is the relation, internal relation between these two resistances which are connected, one in the left gap of the meter bridge and one in the right gap of the meter bridge. Let us now read the second half of the question. When a 10 ohm resistance is shunted across X, one should understand one point here. Shunting means it is connected in parallel. That is the general concept. So what can we write now? When X is shunted with 10, what will be the resultant resistance now? 10 into X by 10 plus X. That is actually towards left now. And towards right, the resistance has not been changed. In the problem also, he did not mention anything about the resistance connected in the right gap. That means what? Same resistance he is continuing again in the right gap. Now left gap resistance is now varied. What is the balance length now? He said balance length is 50 centimeter. Then automatically you can understand the remaining length which is to be called as L2, that also will be 50 centimeter. Then what will be the ratio? According to this we can write 10x by 10 plus x whole divided by y must now be equal to 50 by 50, that is 1. So what we can understand from this one, look at the next step. 10x or 10 by 10 plus x into x by y is equal to 1, I write. You can certainly rewrite the same equation this way. But already we have got what is the value of x by y. It is known to us as 4. So write that value here. 10 by 10 plus x is equal to, right, this is equal to this 4 already we have taken up. So r into 4 is equal to 1, we take it. Then what can I write directly from this? 10 plus x is equal to 40. Then what will be the value of x here? Then x will now be equal to 30 ohm. You can directly understand one value, I have got it as 30 ohm. But already we have got a relation between x and y. X is equal to 4y. That in other words, can't we now write y must be equal to x by 4 please? That x already we have got 30 by 4, which now becomes 7.5 ohm as such. So what are the values of x and y? That is the question. So you can understand directly from this derivation, the total description, x is equal to 30 ohm and y is equal to 7.5 ohm. So x 30 and y 7.5, exactly the same option that is given over there as the second option. So you can understand for this particular question, the answer is going to be the second one. That in the sense we can write this one as B here. That is the correct option for this particular problem as such. So if you look at this one, only point we have to focus on is what do you mean by shunting a 10 ohm resistance? shunting 10 ohm resistance is as well equivalent to connecting 10 ohm resistance in parallel to the resistance already that is existing, that is X over there. That is the only point what we have to remember, and otherwise the problem is not a difficult one, a very, very simple problem, but a very important model as well, this one from this meter bridge point of view. That is problem number 22 in our order. Problem number 23 now. In a meter bridge, a standard resistor of R ohm is connected in the left gap, and two wires A and B are connected one after another in the right gap. That means they are not simultaneously used there. First A is used, then B is used. It's a very clear cut indication there. The balancing lengths measured from left is 50 centimeter for either of them. Whether you are using A over there or you are connecting B across the right gap, in both the cases same balancing length we are getting, that is given 50 centimeter. In fact, here itself one can understand straight away that both have the same resistance. That is the very meaning of it. Okay, let us continue. If the two wires are connected in series and put in the right gap, the balancing length would be how much? That is a question. Now options once again are given this way. First option is 25 centimeter, second option is 33.3 centimeter, third option is 66.7 centimeter, and fourth option is 75 centimeter. The correct option for this is B again, which is 33.3 centimeter as such. How come? Let us check this way. The left hand side gap is filled with a resistance of R ohm. That's what has been given. The right hand side gap, you write that resistance as RA. That is resistance of A, the first wire what he is talking about. And of course, when L1 is given 50 centimeter, it is understood L2 also will be 50 centimeter. Then what can we understand directly from this one? R1 by R2 is now 50 by 50, which is 1. That in other words, R1 is equal to R2 is equal to RA. That means what is the relation between R and RA now? They both are equal. So what I can write now from this one? R1 is equal to RA is equal to R. That is what I can understand directly from the data provided to us in the problem. Now what else he is talking? Once again, in the left gap the same resistance is continued. In the right gap of the meter bridge, another resistance which is RB, that is connected across now. What is this A and B he is talking? A is the first wire or conductor, B is the second conductor. I am considering the resistance of the first conductor as RA and second conductor as RB. That's the point. So I can take it RB. Once again he said same balance length we people are getting. That is L1 is 50 centimeter means L2 also will be 50. Then what I can directly understand again? R1 is equal to RB is equal to R. That is the result. Similar to this I can write over here. That means ultimately what is the understanding here? Whatever the resistance you are connecting in the left gap, same value you are finding for the resistance of the wire A as well as B. So R1 which is equal to R, same is RA and same is RB also. That is what he said. Now what is it he is asking us to calculate? When both A and B are connected in series and used across the right gap, they are now connected across the right gap. That's what has been given. So what else I can write now? R1 again is R. What will now be this value of R2 now, please? R2 is the series combination of RA and RB. But we are sure that both RA and RB, each one of them are equal to R only. So what can we write now? This now becomes simply 2R. Because R2 now becomes RA plus RB, which now becomes 2R. Then let us consider the balance length as L. Then what will be the remaining length from the other end, please? 100 minus L as such. Okay? Just look at that one once again. When we talk about R1, that is R as it is, no change. But in the right gap, he is just making A and B connected in series. In series means what would be the total resistance there? It will be 2R. Now come to the next. Let us consider the balance length as L. Then what will be the remaining length from the other end? 100 minus L as such. Now apply once again Wheatstone's principle over here. It is R by 2R is equal to L by 100 minus L. R getting cancelled. 2L is equal to 100 minus L, which of course you can write 3L is equal to 100. Thereby L becomes 33.3 centimeter. So from left only it is understood. He is just asking you what would be the balancing length. Earlier he said very clearly the balancing length is from left. That means now also the balancing length will be from left side only. Then what will be the value here? 33.3 centimeter. Look at all the options once again. I have already told you the correct option. Second option is given as a 33.3 centimeter in the problem. Therefore, we can straight away take the answer as B for this particular problem. The only thing you need to understand here is when they are connected in series, what would be the effective resistance that should be taken towards the right gap of that meter bridge. That is question number 23. That's problem 23rd one. The correct option for this one, again I repeat, it is 33.3 centimeter, which is the second option over here, that is B as such. Let us switch over to the problem number 24. A cell of EMF 2 volt and negligible resistance is connected in series with a resistance of 5 ohm and a potentiometer wire of resistance 10 ohm. He is asking you 2 bits over here. 1. The potential drop per centimeter if the length of potentiometer wire is 10 meter is how much? That's first bit. The second bit is the EMF of a cell which is balanced by 750 centimeter long wire is how much? The 4 options given are: first option 1 by 1500 volt per centimeter and 0.5 volt. Second option 1 by 750 volt per centimeter and 1 volt. Third option is 1 by 1250 volt per centimeter and 0.6 volt. And fourth option 1 by 250 volt per centimeter and 1 volt. In realistic sense, potentiometer problems, at least 75 to 80% of problems based on potentiometer, you can solve them by considering the concept of resistances connected in series. I repeat once again, potentiometer problems, around 80% of the models, you can solve them by considering resistances which are connected in series. You in fact can understand straight away, when resistances are connected in series, current remains constant, and it is a potential difference that varies from or across resistance to resistance. Based on the same concept, you can deal with this model in a very, very easy manner. Look at once again, 2 volt battery, a cell of EMF 2 volt, negligible resistance, internal resistance is not needed to be taken up there, fine, is connected in series with a resistance of 5 ohm and a potentiometer wire of resistance 10 ohm. That is what has been given there. Okay. Now look at the same description. I consider it like a small circuit. Look at now. I can take a 5 ohm resistance and a 10 ohm resistance. Both are connected in series across a cell which can provide a potential difference of 2 volt. This is given 5 ohm, this is given 10 ohm. Observe carefully, out of the two resistances, 10 ohm resistance is of the potentiometer given. So you should understand this value is potentiometer here. I am just writing PM. That is the resistance of the potentiometer wire. And of course it is given here 2 volt is connected in series across. Then when these two are in series, we can understand pretty well, current remains constant. But potential difference, that varies from resistance to resistance connected in series in that particular combination. So let us take this way. I consider this one as R1 and I consider this one as R2. Remember, R2 is of the potentiometer wire. So I write the first step. Look at R1 is to R2. I take simply the ratio. It is no doubt 5:10, that can be taken 1:2. When R1 is to R2 is 1:2 in series combination, automatically V1 is to V2 also will be 1:2 only. Because according to Ohm's law, V is IR. When I is constant, V and R are directly proportional to each other. So whatever be the ratio of resistances you are finding, same will be the ratio of voltages also. But look at carefully, this is potential V1. The potential difference across 5 ohm resistance is taken V1 here. And across 10 ohm resistance, it is taken V2. So you can certainly understand V2 refers to potentiometer wire. In fact, I want that only. So what can we write from this data? V2 is equal to 1:2 means totally 3 parts. Each one of you can understand 1 part and 2 parts separate. Put together 3 parts. Out of 3 parts, 2 parts of potential difference should be given to that potentiometer wire. You should allocate that much of value. What do you mean by that? V2 becomes 2/3 of the applied voltage. What is applied voltage over here? It is 2 volt, very clearly it is mentioned. So 2/3 of 2, then how much it will now be? 4/3 volt. That is the PD across the potentiometer wire. Now look at the first bit what he is asking for. The potential drop per centimeter if the length of the potentiometer wire is 10 meter. Now all of you can understand V2 is PD across the potentiometer wire and length is given 10 meter, that you can write directly as 1000 centimeter. 10 into 100. Why we are converting? Very clearly he is asking you in the question itself, volt per centimeter he wants, not volt per meter. So convert the meter value into centimeter. You have got 10 meter, that is 1000 centimeter. Now what will be the potential drop? Potential drop across the wire of the potentiometer, that is nothing other than V2 by L. So you can write 4 by 3000, which in turn 1 by 750 what? Volt per centimeter. So for the first option, that is first bit what has been mentioned there, what is the correct option now? 1 by 750 volt per centimeter, that is going to be the potential drop across the potentiometer wire of length 10 meter. Now look at the second bit. The EMF of a cell which is balanced by 750 centimeter long wire. So what is the second bit you people have to remember here? Look at the second one. Length should be 750 centimeter. What would be the corresponding potential difference across that length of the wire? So I once again repeat, when length is 750 centimeter, what would be the corresponding potential difference across that length of the wire? That is what he is asking you. So you all know, according to the basic principle of potentiometer, potential gradient should be constant. So what should I write now? Potential gradient over here is 1 by 750. You can understand well. 1 by 750 is nothing other than potential gradient. You can get that point. Now, this value of V by L is how much? That now must be equal to V by 750. So that means potential gradient in the previous case and potential gradient in the present case are supposed to be equal. Why should they be equal? Means that itself is the principle of a potentiometer. Whenever we apply potentiometer or use potentiometer, potential gradient is constant. Based on that only we just work out the applications on that. So what we can understand? V by 750 is equal to 1 by 750. Both they get cancelled. Then what can we write? The potential now is supposed to be 1 volt. So for 750 centimeter long wire, what is going to be the corresponding potential difference? That is the question. So what will be the corresponding potential difference here? It's simply 1 volt. Now just correlate these two now. Potential drop according to the first bit is 1 by 750 volt per centimeter. The potential difference across 750 centimeter long wire is again 1 volt. So 1 by 750 and 1 volt are supposed to be in the options. So which option is having both the numbers? You see carefully again. The second option gives 1 by 750 volt per centimeter and voltage across 750 centimeter long wire, that is 1 volt as such. So what is the correct option now? The correct answer for this one is the second option, which is B again. So the basic principle, I just remind you once again, potential drop across any length of that wire or throughout the length of the potentiometer wire is always constant. That itself is the basic principle of a potentiometer as such. So the correct option for problem number 24 is second one, that is B. Let us enter into problem number 25. This also is based on potentiometer concepts only. Potentiometer wire of 1 meter length is connected in series to 490 ohm with resistance and 2 volt battery. That means a potentiometer wire is of length 1 meter is given, okay. It is connected in series with 490 ohm resistance and a battery of 2 volt. If 0.2 millivolt per centimeter is the potential gradient, the resistance of the potentiometer wire is how much? Options are given this way. 4.9 ohm is the first option, 5.9 ohm the second option, 6.9 ohm the third option, and 7.9 ohm the fourth option. Correct option is the very first one, that is 4.9 ohm. That is the resistance of the potentiometer wire. But how come? How do we get that? Once again, you just check the same concept. I've already told you, potentiometer wire, whenever that fellow mentions in the problem, it will have certain resistance. So what you can understand is, you take the resistances connected in series. That concept will make your problem much more easier than the direct steps what you used to write. So let us check this way. There are two resistances once again, which are connected in series across a 2 volt cell like this. This is what has been given. What is the resistance of this potentiometer wire? We don't know. That is in fact to be calculated, and I write this one is potentiometer wire, PM, that is the short form of it. And what is the other resistance connected in series now? It is 490 ohm. That I take it as R2 here. R1 I am considering that one as resistance of the potentiometer wire. And R2 the series resistance which is connected as 490 ohm over there. And of course 2 volt he has given very clearly. Now look at, if I consider the potential difference across the resistor R as V1 and across the value of 490 ohm, the potential difference you can take it as V2. Then what is R the question? I go ahead in the same manner as before. 2 resistances are connected in series. Then what can I write? R1 is to R2. That is R is to 490. We do not know the value of R, of course we will be knowing it. Then what would be V1 is to V2? That also will be R is to 490 only, because voltage and resistance are directly proportional to each other when resistors are connected in series combination. When we take V1 stands for potentiometer wire. So I just want from this one the value of V1. R is to 490 means how many total number of parts? R plus 490. So what should I write now? R by R plus 490 into the applied voltage, that is 2. I think all of you might have followed this point. R plus 490 number of parts we have total. Out of them, R parts we have to give to that. So R by R plus 490 into 2. But he is very clearly mentioning length of the potentiometer wire is given 1 meter. That otherwise I can take it as 100 centimeter. So taking these two into account, what will be the potential gradient? You calculate first. What will be the potential gradient now in this case? It is V1 by L. What will be this value now? 2R by 100 into R plus 490. Look at this point carefully now. 2R by R plus 490 by 100, that means into 100. This is the calculated value. But if you look into the problem given, potential gradient is already given in the problem. What is that value given? 0.2 millivolt per centimeter. So this particular potential gradient is equal to 0.2 millivolt, that is 10 power minus 3 volt per centimeter. That means this is given in the problem, and this value I have calculated from the formula. But you all know this value and this value are supposed to be equal. Come on, equate them now. What do you get? 2R by 100 into R plus 490. That is equal to 0.2 into 10 power minus 3. I can write it as 2 into 10 power minus 4. In other words, 2 by 10 to the power 4 I can write. You just look at the cancellation, 2 gets cancelled here. 100 cancels 10 square times. So what is it you people are getting here is the value of R we just want. How much you will be getting? Cross multiply. 100R is equal to R plus 490. Then R will be how much now? 490 by 99. These many ohm. How much this value is going to be around? Had it been 100, you would have got nearly 5. But in this particular case, it will be a little less. So near around 4.9 ohm. So what is the correct option here? It is the very first option that is tallying with it. This 4.9 is the very first option itself. So I can write now the answer for this question number 25, that is A itself. So this is the way we people used to take up the problem based on potentiometer. So most of the problems based on potentiometer can be solved by taking the resistances which are connected in series combination. That concept is enough for us to solve these types of models. And what is potential gradient is common always. It is potential per unit length. That's what is called potential gradient. That's the concept. So this is problem number 25. The option is 1, which is 4.9 ohm. That is the resistance of the potentiometer wire of length 1 meter. That is the point. Let us switch over to problem number 26. It is also on potentiometer, but a different model. Potentiometer even is used to determine internal resistance of a cell also. With utmost accuracy, we can calculate the value of internal resistance of the given cell using a potentiometer. So this is based on that particular concept. A 2 volt potentiometer is used to determine the internal resistance of 1.5 volt cell. The balance point of the cell in open circuit is 75 centimeter. When a resistor of 10 ohm is connected across the cell, the balance point shifts to 60 centimeter. The internal resistance of the cell is how much? A very, very simple concept. When we talk about internal resistance of the cell, that's what we want. It is represented by small r. The formula is known to all of you. L1 minus L2 by L2 into R. Observe carefully, L1 is balance length when only the cell is connected in the secondary circuit without taking the parallel resistance. L2 is the balance length when the resistance which is connected in parallel, that also is made to function. And the value of capital R is nothing other than the parallel resistance's value. The value of resistance which is connected in parallel to that particular cell. So what you should understand here, look at L1, it is given 75 centimeter. L2, it is given 60 centimeter. By 60 again into what is the resistance of that wire connected in parallel. It's given very clearly as a 10 ohm. So you can write this one 150 by 60, which now is 5 by 2. So 2.5 ohm must now be the internal resistance of the given cell there. So seeing the options, first option is 1.5 ohm, second option is 2.5 ohm, third option is 3.5 ohm, and fourth option is 4.5 ohm. These are the four options mentioned there. So which is the correct option for us? The second option is going to be the correct one. So we can say directly the answer for this question is B again. So only thing you need to understand here is what is the formula for internal resistance of the cell. You can even write this equation in other words also, that is E minus V by V into R also you can write. When can we use this formula? This formula can be used when EMF, terminal voltage of the cell, and the external resistance are given separately. So the same formula is written like this also. But in this particular model, this is not going to be useful, and thereby we are taking up the second formula here. So this is problem number 26 for us. Check the next problem, that is 27. Masses of 3 wires of copper are in the ratio 1:3:5 and their lengths in the ratio 5:3:1. The ratio of their electrical resistances is how much? You can write first of all what is the ratio he has mentioned. Masses he has mentioned in the ratio 1:3:5. And what else he has mentioned over there? Lengths are in the ratio L1:2, L2:2, L3. That I can write 5:3:1. Same reverse order he has given, that's all. What is the ratio of electric resistance of the wires? In fact, we know resistance is equal to the value of rho, resistivity. That's what is called specific resistance into L by A. But can't you rewrite the same formula this way? Rho into L square by volume, please. And you all can understand straight away, volume can be written as mass by density. So what can we write now? This is rho L square into density divided by mass. So you can understand well, according to the problem given, all the 3 wires are made up of copper. What is it giving you? The idea of giving the name of the material. One can understand density is constant and specific resistance also is constant. So what can we write now? R is directly proportional to L square by M. That is the formula. So what can we write now? R1:, R2:, R3 is equal to L1 square by M1 is to L2 square by M2 is to L3 square by M3. That is the total ratio. What are the values given? You know, L1 square, it is now 25 by M1, that is 1. Next, L2 square, it's 9 by M2, that is 3. Then L3 square, that is 1 by the value of M3, that of course he has just given you the resistance M3 is 5 here. Write it as it is. Now you can rewrite the same this way. 25:3 is to 1 by 5. Come on, arrange this order. It's now 125 is to 15 is to 1. Just search for that option now. He has given you 4 options there. 1:3 is to 5, the first option. 5:3 is to 1, the second option. 1:15 is to 125, the third option. 125 is to 15 is to 1, that is the fourth option. So what is the correct option now? The correct answer for this one is the fourth one, that is D, according to the options given in the question. Only thing you should understand here is resistance, when we consider in terms of length and mass, is proportional to L square by M. That is the concept you need to understand. So if you can get that idea, this is not a big problem, a very, very simple model as such. So this is problem number 27. Now the next number, 28th problem. Two cells having EMFs E1 and E2, he gave which is more also, E1 greater than E2, when placed in series, produce null deflection at a distance of 204 centimeter in a potentiometer. When placed in opposition, very simply speaking, what is this wording? Opposition. When one is reversed in the direction, that means they are not in series now. One is reversed. That is the idea. They produce null deflection at a distance of 36 centimeter. If E2 is 1.4 volt, what is the value of E1? 4 options given once again. First option 14 volt, second option 10 volt, third option 4.2 volt, and fourth option it's 2 volt. So correct answer for this one is no doubt 2 volt. That is the last one. That is the fourth option. That's correct. But let us check once again. In this case, we are just making use of two cells connected in series this way. And the balancing length what we people have got over here, according to the problem given, it is 204 centimeter. So what you should understand, if I take this one is of EMF E1, this one is of EMF E2, then what will now be the effective EMF, please? It will be E1 plus E2. And what will be the corresponding balancing length now? 204 centimeter. Now what did he say in the second part? One cell is reversed. They are opposing each other. Opposition means what? One is opposing the other cell here. So you can understand this one as E1 and this one as E2, positive, negative, negative, positive. Then how to write the effective EMF now? It is E1 minus E2. And what is the corresponding balance length now? It is given simply 36 centimeter. That's what has been given. So according to the principle of potentiometer, the potential gradient should be constant. So what do you mean by that? E1 plus E2 by L1, E1 minus E2 by L2 are supposed to be equal. In other words, I write the same this way. E1 plus E2 by E1 minus E2 is equal to L1 by L2 I can write. But of course, componendo dividendo, that concept of mathematics when we apply here, we can write E1 by E2 is equal to L1 plus L2 by L1 minus L2. What is L1 plus L2? You look at 204 plus 36, that is 240. What is the next one? 204 minus 36. 200 minus 30 is 170. 170 is okay. 204 minus 34 is going to be 170. So it will now be, how much you will be getting here? 204 minus 36 over here, right? 204 minus 34 happens to be 170, no doubt. Now 170 minus 2 again, 160, 240 by 168. That's what we can write. Now what is the concept he is asking you? If E1 is, E2 is given 1.4 volt, then what is E1? So what can we write now? E1 by 1.4 is equal to 240 by 168. So what will be the value of E1 now? It is 240 by 168 into 1.4. If you simplify this one, exactly you will be getting 2 volts for that. You can even check that value over here. Exactly twice this value will be getting in the numerator. So if you look at that, 2 volt is the value of E1. So what you can understand, out of all the 4 options, the 4th option is given 2 volt. So what can we write now? The correct answer for this particular problem is D now. So only thing you should understand here is, when one cell is reversed, automatically EMF is going to become E1 minus E2. So E1 plus E2 by E1 minus E2 is L1 by L2. Applying the concept of componendo dividendo, you can write E1 by E2 is equal to L1 plus L2 by L1 minus L2. This is the major equation which one has to remember to solve these model problems based on potentiometer as such. So this is problem number 28. Problem 29 now. 5 cells, each of EMF E and internal resistance small r are connected in series. If by mistake one of the cells is wrongly connected, the equivalent EMF and internal resistance of the combination are how much? He gave 4 options. First option is given 5E and 5R. Second option 3E and 5R. Third option 5E and 3R. Fourth option 3E and 3R. The correct option for this one is the second one. But how? Once again, look at once again, when cells in series, suppose if I consider, then effective EMF is going to be N times E if I say N cells are in series. If I take for example N cells are connected in series, what would be the effective EMF? N times E. Quite simple to understand. Now in this case, N is given 5. So naturally what we expect? Effective EMF is supposed to be 5E. But he gave a wonderful clue there. He did not connect all of them in series. By mistake, one cell is reversely connected. Wrongly connected means what? It's reversely connected. All of us we can understand straight away. When one cell is wrongly connected, that cell cancels the EMF of another cell also. So what happens ultimately? When one cell is wrongly connected, 2 cells in all will now be cancelled in terms of EMF. So what we should understand? If M cells are wrongly connected, observe this wording carefully. If M cells out of N are wrongly connected, then effective EMF will be N minus 2M into E. Why we are writing 2M just now I have explained you. One cell wrongly connected means it cancels the EMF of another cell also. So overall in the total system, 2 cells they lose their EMF. including this one. This is one more. So totally 2 cells will be off. As far as EMF is concerned, remember this point carefully. Resistance will not vary. Resistance will be the same. So you can understand here N is 5. M is 1. So this will be now 2 into E. Then how much it will be? 3E. So what will be the effective EMF now? When one cell is reversely connected, effective EMF now becomes 3E. Fine. But what would be the effective internal resistance? That's what he is talking. So internal resistance effective value will never be cancelled, I have already told you. A resistance, when I show you this way, this is resistance R. If I say, even if I reverse it and ask you also, its resistance will be the same. So resistance will not have a negative value. Resistance will never be varied. So ultimate value is this: all the 5 cells have got internal resistance. Therefore, total value of internal resistance of the system now simply becomes NR. So here N becomes 5. So you can say 5R, that is internal resistance. 3E is effective EMF. 5R is effective internal resistance. Look at the second option now. It is given 3E and 5R. That is the correct option for this model question. So what we can understand here, the answer for this one is the second option again, that is B. So only thing you should understand is when one cell is wrongly connected in any circuit by any chance, then that cell gets another cell also cancelled in terms of its EMF. So ultimately 2 cells will be off in terms of their EMF. That is the concept one should understand from this problem number 29 as such. Check the problem number 30. This is a circuital problem once again. The numerical value of charge on either plate of the capacitor C shown in the circuit is how much? Is just giving us 4 options once again. CE the first option. CE R1 by R1 plus small r the second option. CE R2 by R2 plus small r is the third option. CE R1 by R2 plus small r the fourth option. What is it he has given? Let me draw the circuit first. He is talking about a cell connected across a resistor here in the first branch. Another resistance is connected across the system in the second branch. And here he has mentioned a cell this way with an internal resistance small r like this. So this is the capacitor what he is talking about. See, these 3 are resistances. This is given as EMF E over here. This small r in fact is internal resistance of this one. And what are the values he has provided here? You look at, this is R1 and this one is R2. This is the given circuit. But you can certainly understand one point. When I make the system on, current will never enter into this branch. Reason is better known to every one of you. Cell, this is a capacitor. Capacitor will never allow current to pass through. Therefore, no current will be seen in this branch. Then what will now be the effective resistance of the system? These 2 in series. So it becomes R1 plus R. And what will be the effective EMF that is given over here? That is E. Okay, so now this is actually the concept what he is talking. So you can say effective resistance will be taken up only by considering these 2 resistances, and EMF is E. This is what one should remember from this type of a circuit. But for my easiness, I just make this circuit in a different way. It's going to be easy for you as well. Look at what I do in this case is, I take this capacitor, I take this resistance, I consider one more resistance here. This is given as R2, this is given as R1, this is given as C. Now you can say this is the external resistance small r, and here is the cell that is connected across. This is the one. E is the EMF. Same circuit, I have redrawn that one like this. What for you can better understand? Whatever is the potential difference across this R1 you find, same will be the potential difference across this branch also. Therefore, what I can write is, what is the ratio of their resistances? R1 is to R2. I write that one as R1 is to small r, because this doesn't come into picture because no current that passes through that. And what will be the potential difference across these two? That again will be having the same ratio, R1 is to R. So potential differences are in the same ratio of resistances when they are connected in series. So what you should understand here, current is entering this way, that current is passing through this one, and it is just exiting through this one. That is actually the very idea, no current that passes through this. So what is the PD across these 2 points? I take V1. What is that value now? R1 by R1 plus small r into the value of E. So R1 by R1 plus small r into the value of E. That is the potential difference across these 2 points. When I talk about potential difference across R1 is this much, potential difference across the second branch also will be the same. Why should it be like that? Because these two are in parallel. In parallel combination, potential difference is the only parameter which remains constant across all the branches. So across this one also, the potential difference will be the same. Therefore, I can write now charge on C. What is charge actually? Q is equal to CV, that is the formula. Which V to be taken now? It should be taken as V1, that is the concept. So simply substitute this value here. It now becomes C R1 E by R1 plus small r, that is the formula. Look at now here, C R1 E by R1 plus small r. Which option that is giving you this result you look at? Second option, CE R1 by R1 plus R. Is it not the same option what we people have got here? So what is the correct answer for this one now? The answer for this one again is B, that is the second option. So what we people should understand from this one is, cell always is connected in series, one area, and internal resistance always will be in series with the remaining system. Second point, whatever is the potential difference across R1, same will be the potential difference across the other branch also, because both are connected now in parallel to each other. So that is the concept. So these 3 points if you can identify, you can directly get the amount of charge on the capacitor C that's given in one of the branches of the given circuit. This is problem number 30. The correct option for that one is B, that is the second one. Let us switch over to the next problem, that is problem number 31. In the network shown, the potential difference between A and B is how much? He just has given us a small circuit. Out of that, he gave the values of R, R1, R2 and R3. Each one is 1 ohm. He gave E1 is 3 volt, E2 is 2 volt and E3 is 1 volt. What are the options given? Simply in the sequential order all numbers he has given. First option 1 volt, second option 2 volt, third option 3 volt, and fourth option 4 volt. Let me draw the circuit what has been given to us first. We have been given a resistance here, connected to that a cell like this. Likewise, he took 3 branches. The third branch is like this. And what he has done is, these two he has connected this way. These two he has connected this way. And again here, one more resistance that is connected like this. And of course, he has said in the problem, these two are the points across which the resistance, the EMF is supposed to be calculated. So what did he say now? This is the point A, this is the point B, this is the value of capital R. This one given R1. He has given the values R1, R2, R3 like. This is R2, this is R3, this is E1, this is E2, this is E3. Negative, positive, negative, positive, negative, positive. But let us write the values given first of all, because that is more important for us. E1 is given 3 volt, E2 is given 2 volt, E3 is given 1 volt. Next, R1 1 ohm, R2 1 ohm, R3 1 ohm, even R also is 1 ohm. His question is, what is the potential difference between the points A and B? Potential difference means what you have to calculate? Effective potential difference across the system you have to calculate. If I see these 3, I can understand straight away positive sides are all towards one end. So you will be finding a current I1 across this one, I2 across this one, I3 across the third. All the 3 currents will mix up over here to give out the total current as I. So according to the first law of Kirchhoff, you can apply at this junction, I must be equal to I1 plus I2 plus I3. And what is I by definition or directly by formula? I is equal to E by R. So you can write directly E effective by R. What is R now to be called? Effective internal resistance. So what is I1? It can be written as E1 by R1, I2, E2 by R2, I3, E3 by R3. You can now understand from this what will be the effective EMF. E1 by R1, that is 3, E2 by R2, that is 2, E3 by R3, that is 1, into R effective. What is this R effective value? You people should remember first. All the 3 resistances are now connected in parallel. Then how to calculate R effective here? R effective value is nothing other than R1, R2, R3 by R1, R2 plus R2, R3 plus R3, R1. That is the formula. And you know very well R1 is 1, R2 is 1, R3 also is 1. 1 into 1 into 1 it's 1. This is 1, this is 1, this is 1. So how much it will now be? 1 by 3 ohm. That value, come on, you substitute it here. 3 plus 2 plus 1 is 6 into 1 by 3. How much it will now be? 2 volt. So what is the effective EMF of the system is the question. I have applied first law of Kirchhoff at this particular junction point. Therefore, you can understand straight away at this point I1 plus I2 plus I3 must be equal to I. and I should be effective EMF by effective internal resistance. Similarly, E1 by R1 is I1, E2 by R2 is I2, E3 by R3 is I3. And what is effective internal resistance formula? R1 R2 R3 by R1 R2 plus R2 R3 plus R3 R1. This value I have got 1 by 3. That after substituting it here, I have got 2 volt. 2 volt, if you look at in the options, the second option is given 2 volt. So what is the correct answer for this particular question now? It is again B. That is the correct answer for this particular problem. Of course, circuit is looking big, but concept wise if you go, it's not a big problem, a very simple problem, but a very important model there where we people are applying the concept of first law of Kirchhoff. That is problem number 31. Problem number 32 now. The given 4-terminal network is a part of a larger circuit. He gave a small circuit there, which he is explaining that it is a part of a very big circuit somewhere. The points A, B and C are at the same potential. The potential difference between any one of A, B or C and D is 40 volt. The potential difference between A and O is how much? The options are given once again. First option 10 volt, second option 15 volt, third option 18 volt and fourth option 20 volt. The correct option for this one is the first option, which is 10 volt as such. Look at the circuit given first. Let me draw the circuit what has been given by him first. He gave 4 resistors like this. And what he said is, each resistance is R. This is the point O. And he has mentioned over here, this is one point, this is another point, this is the third point. What are those 3 points he is talking? One is A, one is B, one is C. And this point is the other one. So A, this one is B, this one is C, this one is D. And he has showed that the current is entering towards the point O in all the 3. And here the current is just moving away from the point O. These are the directions given. And he has given us a wonderful clue in this problem. All the 3 points A, B and C are at the same potential. That is a wonderful clue for you. So what we can understand here, same circuit, you draw it like this. Simply you take 3 resistors in parallel. All the 3 now are connected across the third one. That is of course connected in series to the fourth one. So if you take this one as R, this one as R, this one as R, these are the points what have been given as A, B and C. This is the point that is given as D and this one is R again. What is the value he has provided, you see first. Potential difference between any one point out of the 3 and the point D is given 40 volt. So I can understand here 40 volt is the potential difference across A and D or B and D or C and D. That is what has been given. So let us once again write this 40 volt divided among these 2 resistances. Come on, divide them. How? The point is, let us take R1 is to R2. This is all R1. This is R2. I am just taking 2 resistances in the system. These 3 are connected in parallel. Therefore, the effective will be R by 3. This is in series. The value is R. So R by 3 is to R. This is the ratio of these 2 resistances. This is single resistance like R1 I have taken, this is R2 I have taken, this is R by 3, that is R. Then what would be the ratio there, please? 1:3. When ratio of resistances is 1:3, even the ratio of potential differences also will be 1:3 only. So if you take this point as O, what is the PD across A and O? He is asking. A and O means you need to know about V1. So what will be the value of V1, please? V1 is 1/4 of the total voltage. Why again 1/4? 1:3 means totally 4 parts. 1 part and 3 parts, put together 4. Out of 4 parts, 1 part you have to provide to this. So is it not 1/4 of the total applied voltage? What is the applied voltage given here? 40 volt given. Therefore, 1/4 of 40 now becomes 10 volt. So what is going to be the PD across A and O now? It is a 10. PD across B and O also will be 10. PD across C and O also will be 10. Reason? All the three are connected in parallel. When resistances are connected in parallel, the potential difference is the only parameter which remains constant across each and every resistance there. So what we can understand here, between A and O, the potential difference is now going to be 10 volt. Look at the options given. Very first option itself is given as 10 volt for us. So what can we write now? The key or the answer for this one, that is going to be the very first answer, that is A. So option A is tallying with 10 volt here. So the correct answer for 32nd problem is going to be 10 volt, which is given in the first option as A in this problem.